Okay, great. Huge pleasure to be here and to be talking about Pluto. I'm going to give you a whirlwind tour of why we went to Pluto, what we found there, and all the cool pictures and so on and so forth. So this picture is actually from before the flyby, and it was an artist's picture based on what we thought we might see, with the moon Charon there, and a surface with ice. Of course, the spacecraft did not get anything like as close as this. I'll show you how close it really got. And the sun, which is about 1,000 times weaker than the sun here at noon on Earth. So let me talk a little bit about, wrong button. Let me do this. Let's talk about Pluto, discovered back in 1930 by Clyde Tombaugh, and has not gone halfway around the sun since then. And you can see here from various important space activities, and then the discovery of Charon in 1978, and then the closest Pluto ever got to the sun in its this last orbit was 1989. And some of you may remember that we celebrated this with a keg of beer on the lawn outside Dwayne, which shows how long ago, because you'd never be able to do that now. Okay. So we started working back then on a mission to Pluto, and what was very important was along the way was the discovery of the second object in the Kuiper Belt, because now we know there are many objects out there near Pluto, all sorts of different colors and shapes and sizes. This is 1,000 kilometers for scale. I'll show you here in a little bit more what the different sizes are. But think about this. This is a movie made by Alex Parker since the discovery of the second Kuiper Belt object. Here is Pluto, the larger one, and then this is the orbit of Neptune out here. You can see there are now thousands of these objects, a couple of thousand of these objects that are spread around, and the astronomers in the audience might want to think about why we don't find them in there and the other side, or why it's hard to find them in those directions. We'll come back to that at the end of the talk. But what's interesting is that when you tip this on the side, you see that these are all scattered. They're not in the plane of the planets, the ecliptic plane, they're scattered out of it. And that is an important factor. But the discovery of these, let me hit the right button, the discovery of these has been important. It really provoked us into thinking, if we go out there, we're not just going to look at Pluto, we're going to look at a representative of a large number of objects out there. So you see all these different colors, different shapes, some of them have moons. And for comparison, let's look at the largest asteroid, the asteroid belt series taken by NASA's Dawn mission, and you can see the comparison. So Pluto is much larger than Ceres. Now, when we set off to go to Pluto, and until we got there, I thought we would see something a bit like this, with a few impact craters, maybe a lighter patch or a darker patch, and you'll see what we really saw. Okay, so here we are. We have Pluto and Charon. Charon's nearly half the size of Pluto. And for scale, we have the Earth. So these are all to scale. This is where they would be if you could put them close to each other. This would be the real separation and the real sizes. And in terms of masses, Charon is about 1/8 the mass of Pluto, and Pluto, there would be 457 Plutos within the mass of the Earth. But what's interesting is, when you think about the mass of Pluto and the mass of Charon, I've made a scale model here that you can maybe see, and I put some pennies on the Pluto side to make it balance, so that's about 8:1. And you can see the center of mass, the balance point, is outside Pluto. So that is the point about which they both spin, like this. Okay, so they gravitationally spin around each other. And having a stick there holding them together, because I can't simulate gravity on this scale, is actually quite realistic, because they're spin phase locked, which means that somebody on this side of Pluto would see what when they look in the sky to look at Charon? Always. It would be up in the sky in the same place, okay? And if you were on this side of Charon, what would you see? You'd see Pluto always in the sky. Now, what if you were here? you would never see anything, right? So this is a really bizarre system where you wouldn't see the moon on the other side. And they're phase locked, spin phase locked like this with a 6.4 day spin period. Okay, so that's important when we think about how this system works. Now, these were the best pictures that we've ever taken from the Earth, either using ground-based observations or Hubble Space Telescope, or all the ingenuity we could make. And so we could see there were dark areas, light areas, browny areas, but, you know, impact craters, canyons, you can't tell, right? I mean, it's just a blob. Okay. So we could tell the rough colors. Pluto was sort of reddish, Charon was brownish. We knew their densities because we could use Newton's laws to get us a sense. We knew how fast they were spinning around each other. We knew their rough sizes. We could get their densities, so roughly half rock, half ice. And we knew their temperatures. And you can measure it in Kelvin or Celsius or Fahrenheit. It really doesn't matter what temperature scale you pick. It's damn cold. Okay. So, we knew all that before. And what is it really like? Well, the answer is we've got to go explore. And so back in 1989, Alan Stern and I started working on this, and there were, you know, we tried to persuade NASA to go to Pluto, and it was difficult until more Kuiper Belt objects were discovered. But around then, we started to have some missions designed. They'd be designed, and then NASA would realize that it was just ridiculously expensive, and they'd cancel them again, and then design another one that would, and so on and so forth. And then eventually, there was in the New Frontiers line, which is a competitive PI-led mission line that was started back in 2001. We proposed a New Horizons mission to go to Pluto. And so this is at the top, our site review, making the case to NASA to send a spacecraft to Pluto. We won that proposal. We started building, spinning it, testing it, shaking it, baking it, all the usual things we do with spacecraft to make sure it's going to survive. But this gives you a sense of the size, okay? So, you know, about the size of a small baby grand piano. So what have we got on it? Well, we have over here the radioisotope thermoelectric generators that provide about 200 watts. That's using plutonium-238 to provide heat, which we turn into electricity to power the spacecraft. We have an antenna here that will communicate back with Earth. It's about 6 foot across. And we'll use the radio experiment to do occultations of the atmosphere to give us some sense of the atmosphere, as well as communicating and sending all the data back. And then we have some cameras. We have the long-range camera here, which will take those high-resolution pictures, which you'll see just in black and white. And then Ralph here, which was built here in Boulder, Colorado by Ball Aerospace. At least a lot of it was built here. And that takes color pictures, wide angle and color pictures. Now, in the UV, the ultraviolet, we have an instrument called ALICE that will look back at the sun and look at stars through the atmosphere. And we have two instruments, PEPSI and SWAP, that will look at charged particles, the solar wind, and the interaction with the solar wind. But the most important of all of these instruments here is the student dust counter that was designed, built, tested, operated, and the data analyzed by students here at LASP in this building. And this is the first time that a student-built instrument has gone out into the outer solar system to make exploration. So, what does it do? It's sort of about this size, and it has a bunch of plastic, very special plastic, which measures impacts of very small micron-sized dust particles that will impact these pieces and be counted as we move out through the solar system. And that will tell us how much material, how much dust gets produced when objects in the outer solar system bump into each other and generate dust, or comets that break up and come through the outer solar system. We will measure that with the amount of counts that we measure on this. Okay, so Is there anybody from the SDC here in the room, by the way? Okay, so now I can ask you this question, because if they weren't, I have to tell them to keep quiet. How many counts do you think they measure on the way out through the solar system? How about 10 a day? 100 a day? 1,000 a day? Pieces of dust. You're flying along 33,000 miles an hour. How many dust impacts do you think you measure?
I heard it was a couple 100,000 or something.
100,000 a day? Hmm. How about 1 a day? In fact, that's a bit optimistic. It's more like 1 every 3 days.
Oh, really?
Yeah. Space is empty. Pretty damn empty. Not completely empty, but pretty empty. Okay. So, yeah, measuring very few particles out there, but very useful to make those measurements throughout the solar system to get a sense of the distribution of this material. Okay. So eventually we get to launch day, January 19th, 2006, and a bunch of the students from CU were there all lined up to watch it go. It didn't actually go the first day, it went the second day, but we were on our way. Now, just before launch, about a month before launch, Hubble found 2 more moons. And then a little bit further out, on our way there, we found another 2 moons. So now we've got 4 moons, plus this 5 moons, plus Pluto, 6 objects to look at. So we've got to change our plans and do things a little different. Okay, but now we begin to go, uh-oh, maybe we've got a problem here. Because by the time we get there, Pluto and the moons are spinning around like this, and we're going to go through the plane of these moons. And we're beginning to think, maybe they've all been broken up and there's a whole load of debris in that ring plane that we're going to have to fly through, but we're not going to get the data back immediately. So, you know, we would not see any of the data. So we started to panic that we might hit a cloud of debris, and we started to make alternative plans and so on and so forth. Now you have to remember we actually had 9.5 years to get there, so that's 9.5 years of worrying. You know, so, okay. So I want to take a quick time out because we have to think about, you know, why on earth do we go to Pluto? Yes, it's cool, it's neat, you know, we want to see what it looks like. But it plays a much bigger role, and that is we want to understand how clouds of gas, in this Hubble picture out here that we know are out there in space, and we know that they collapse to form solar systems. And we want to know how that happens. And we think understanding something about the Kuiper Belt is important. So we need to think about how do we make solar systems. And this is from a standard textbook where you have a big cloud and it collapses either because it's pushed by a supernova or it just collapses due to its own gravity. And it begins to collapse and spin up and form a disk. And then you have your proto-sun in the center that's nice and hot, and then the gases around it are hotter, and it gets cooler further away from the source of heat at the center. And in close to the star, you will have rocks and metals condensing out because they become solid at quite high temperatures. But as you move further out beyond the frost line, water, which is an extremely abundant material in this cloud, oxygen being the 3rd most abundant element in the universe, then you will have ices, and a lot of ices, that will form clump together to form the cores of the giant planets. So this is our standard story of how we make small rocky planets close to the star, and then giant planets where you have ice cores with hydrogen, the most abundant element, pulled in to make big gas giants. So this is all very good, but what about this thing out here? What about the Kuiper Belt? Well, that's the original idea. In the past 15 years, a lot has happened. One thing that's happened is we've looked at all these other solar systems around the universe. We've seen a bunch around other stars, and they're very different to our own, including the probability that a lot of the large planets have migrated in towards the star. Another possibility is we think, well, it's very difficult to make Uranus and Neptune out at their current distances out here in the outer solar system, within the age of the solar system, because things out there move very slowly and it takes a long time to accumulate to make a planet. So some very ingenious people about 15 years ago started to take numerical models, and they said, what if we put a bunch of planetesimals around, and then we put Jupiter and Saturn, Uranus and Neptune in close, around where Jupiter and Saturn are now. And then they let this run for some time and see what happens. Okay, so this is what happens over a period of millions of years. So remember, we have Jupiter, Saturn, Uranus and Neptune, but all in pretty close, and they begin to scatter these objects around. And you keep waiting and waiting, and they're working around and wobbling around and interacting in some way, and kaboom, kapowie. All of a sudden it goes unstable, and you can see Uranus and Neptune have been moved out, and these objects have been scattered. Okay, so this is a model from Hal Levison and Catherine Kretke, who have been doing these kinds of models and doing a bunch of them to say, can we form our solar system in a way that is reasonably realistic, produces Jupiter and Saturn enclosed, Uranus and Neptune further out. But also this has several other advantages. You can make Uranus and Neptune at their current orbits. You can scatter objects into the Kuiper Belt. You can deliver water to the Earth, though that isn't necessarily the only way to do it. It's one way of doing it. But then it tells us that, going out and looking at the Kuiper Belt and learning about the Kuiper Belt, learning about Pluto and the Pluto system, are testing these ideas of whether or not this is really how things worked in our solar system. So that's why we're doing it. It's not just because it's cool to see Pluto, but it actually is representative, we think, of the Kuiper Belt. Okay, so we've launched. We go get we get a shortcut by flying past Jupiter. That saves us 3 years of flight, which is huge, right? Using the gravity assist of Jupiter, and gets us out to Pluto in 2015. Okay. So this is the flyby geometry. And you can see this. We're moving at 33,000 miles an hour. One of these tick marks is 10 minutes. And so it takes about 4 hours to go through the system. 4 hours. We've taken 9.5 years to get there. And we're going to go right through the system really quickly. Okay. But notice this. The communication time with our radio dishes between the spacecraft and the Earth is 4.5 hours. Right? So we can't tell it, oh, turn left, turn right, look over here, do that. This little thing is a robot. We tell it what to do. It goes on out there, it takes all these pictures, click, 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 turns back to Earth and says, I'm okay, I took the pictures, what do you want me to do next? Right? Okay, so it really gives you a sense of this is, most of space business is working with robots, but this really gives us a feel of being a robot, because there's no way you can change along the way. Okay, we have to pre-program the whole lot. And the way we did it was to go so that when we look back at Pluto, we would have an occultation of the Earth and the Sun, both of Pluto and Charon, and I'll show you that movie of that a bit later. The last thing I've put on here is that we've got a 3 kilobits per second transmission rate. So remember that antenna, it's got a power of about a 20 watt antenna. So think of a refrigerator light bulb, that kind of power. Sending that back across 33 times the distance between the Earth and the Sun. So we have big dishes on the ground, but it's a slow rate. I don't know what your best internet rate is. Well, I don't know what, 50 megabits per second, right? If you got less than that, you would be complaining to Verizon or whatever it is, right? So this is a really slow transmission rate. Another thing that you need to think about is that we designed to move about 10 times, 9 times the size of Pluto further away, 9 times the radius of Pluto away. That'll be important in a minute. You'll see why we picked that distance. Okay, so here we are. This is a movie, a simulation, and you can go to Eyes on the Solar System and see this at nasa.gov. And so this is the spacecraft, the little robot, doing what it's been programmed to do, take pictures of Nix and Pluto and Charon and Pluto and Charon and go back to Nix and then more and then so on and so on and so forth. And so it's doing all these click, 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 but of course the antenna is pointed away from the Earth while it's doing all this, and then eventually at the end it'll turn around and it will communicate with the Earth. Okay, so this goes on for quite some time. Okay, so let's think about how much light there is at Pluto. And there's a really cool thing that you can go to, a little app that we'll call Pluto Time that you can go to, and it will tell you on that date at where your location what time of day you should go outside and take a picture and get a sense of the right amount of Pluto light, right? Because of course it's 33 times further away. Square that, you get a factor of 1,000 weaker light out at Pluto than we have here at noon on Earth. And so that's, you can read at those with that light level, right? But that means that we have to design our camera exposures so that we could go closer, but moving at that speed with long exposures, we'd get a smeared picture. So we design the exposures so that and the distance, so that when we take a picture, we get a clear, unblurred picture with the right kind of exposure. Right, okay. So what did we see? Well, on approach, of course, Alan Stern was getting all excited. We're going to get better pictures than Hubble. It's going to be cool. It's going to be great. And each day there'd be a new picture. Look at this, look at this, look at this. And the geologists were all going, oh, I see impact craters. Oh, I see volcanoes. And those of us who do particles say, you know, it's a fuzzy picture, guys. It's a fuzzy picture. Okay. But, you know, they were getting excited. So what do? You've got to realize, okay, so we've told the robot, off you go, take all the pictures, and then we've got to wait. We know that it's flown past Pluto, but we have to wait and wait and wait to get the pictures back and to hear that it's happy. So what do? While we're waiting, we took selfies. This actually was a really cool picture. It shows all the women in New Horizons, and this is actually about a quarter of the team. This is really a high fraction of the team compared with, say, Voyager, where there was probably, you know, 1 or 2 out of 20. And so this is a good ratio. It was good fun. Okay. We also had a jamboree with all sorts of famous people phoning in and blah, 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 and hoopla. Yeah, I mean, why not? A lot of people were excited. It was a great day. And then finally, Alice Bowman, the Mission Operations Manager, or MOM, was talking to the spacecraft, or listening to the spacecraft, and the spacecraft announces, not only is it well and happy, didn't hit a debris cloud, but the memory are full of data. So we're really excited. And I think it really is historic in terms of getting the data back from such a distance. And look at the cultural difference between 1969 and 2015. Kind of interesting, isn't it? Okay. So then we went nuts. Okay, so some photographer took this picture and it was sent around the globe to my embarrassment, but enthusiasm, because knowing that was the memory banks were full, the memory storage was full, I was just really excited. That was what I wanted to hear. Okay, so what did we see? Okay, let's look at the pictures. So we knew there were dark areas and light areas, but we really didn't understand that there would be this amount of geology. Really exciting stuff to see. The areas that are really white, darker areas. We can see some impact craters and so on. So let's have a look at some of these things. They have some names. We called Tombau region, this sort of heart region, after Clyde Tombaugh, who discovered Pluto. And then we started naming things after various space-related things. Now, remember, all Pluto names are informal. They're not official, they're not approved. The IAU has not given its blessing, as if we care what the IAU thinks about Pluto. So, you know, we got to put that there. But, you know, okay, done it. We can move on.
Weren't they the ones that downgraded it?
Yeah. Hey, dwarf people are people. Dwarf planets are planets. Okay. Okay, so let's think about this. Pluto and Charon spin every 6.4 Earth days. We have a 4-hour flyby. We're only really going to get close to one side. What are we going to pick? Well, we decided to pick this region because it had, we thought, the biggest contrast between light and dark, which suggested really interesting geology. That was our guess. We also picked this light area because if our exposures were wrong, we knew we would at least get some good exposures there, right? Because it's light, it's easier to take pictures of lighter things. So that's really where we flew by. We didn't know it looked like a heart when we programmed it, honest. We didn't, really. Okay. So we're going to have fuzzier pictures on this part. This part is in permanent darkness, and we get a little bit of back-shadowed pictures of those from the scattered light. We can see some down there, but mostly we're going to take with the high-resolution pictures are of this part here. Okay. So we have to think about this. We knew the density pretty well. It's sort of, if you look at it more accurately, you end up with something like 1/3 water ice and 2/3 rock, and the density is a little less than twice that of water. So this tells us that there must be a layer of ice on the outside over the rock that is about 180 miles or 300 kilometers. That is a really thick layer of ice. So when we look at this planet, we are not seeing rock, we are seeing ice. And what we're seeing is water ice that acts like rock. It is so solid at these temperatures that it acts like rock, okay? Very rigid. It cracks, and as you can see here, right, here's some cracks. We see impact craters and so on. But this is on ice, where water ice acts like rock at these temperatures. Okay. We also see nitrogen ice, methane ice, and carbon monoxide ice. So the water ice is the stuff that's rigid and doesn't flow. It acts like rock on Earth. And the nitrogen ice, the CO ice and the methane ice flows. It's much less viscous. It can flow like water ice on Earth, or flow like silly putty or something like that, okay? So over time it will flow. So we see glaciers, and this is Sputnik Plano, and we'll show you some of the features here. We can also use the Ralph instrument to look at the spectroscopic features in the infrared, and we can work out where exactly the nitrogen ice is. This is Sputnik Planum here with some elsewhere, CO as well, and also methane, which seems to be moving around more, maybe having seasonal motions across the planet, because Pluto has very complicated seasons. And so we will see other places where it looks like methane forms a sort of dusting, a frosty dusting at the higher altitudes. When we look at water ice using our spectroscopic studies, we find that water ice is in the dark areas, and it's absent from the Sputnik Planum area where the nitrogen ice, the fresh area, is. Then there's the black stuff. We'll come back to the black stuff. It doesn't look like water ice when you look at, it looks all black and gooey, right? We'll come back to that in a minute. Okay, so this is the black and gooey stuff. Remember, this is actually water ice covered in black gooey stuff. Here is a picture zooming in here where you have some frost, like I mentioned, at higher altitudes around these impact craters. Lots of impact craters tells it's quite old. We see some cracks here that tells us it's broken up. Maybe on freezing it broke up, on expansion, in this area over here that's relatively old. We then look at a slice here that goes from Sputnik Planum over towards that old region, and you can see you're going from very young. In fact, there are no impact craters that have been found anywhere on Sputnik Planum. So that tells us it's relatively young as an area, geologically speaking. So we have young areas here. Then we have these big blocky areas, which I'll talk about in a minute. And then we have a plain with impact craters further away. Okay. So those blocky areas, right on the edge of Sputnik Planum, turn out to be water ice. And water ice actually is a lower density, even though it's more rigid than nitrogen. So it would all actually float, which is really bizarre to get your head around. So these are very weird substances acting strangely at these extremely cold temperatures. But look at these elevation scales. These mountains have the difference between the bottom and the top of these mountains is comparable to the Rocky Mountains, right? These are good 14ers. I haven't done the exact calculation, but somebody can do it in the room, I'm sure, very quickly. These are comparable to 14ers. These are big mountains that are sticking up, made out of water ice. Blocky. Now, how they got to be there, we don't really know. Maybe when there may have been a big impact crater that formed Sputnik Planum, maybe they were kicked out. We really don't know where they came from. Okay. So when we look at Sputnik Planum, what's kind of interesting is we see these polygonal cells. And we also see flows around this bit that was sticking up and into the valleys and so on. So this is a glacier. It's a big glacier, and not only is it flowing on the edges, but we also think that there are areas, these polygonal areas, are convecting systems that are turning over like convection cells in a bubbling porridge or in soup or whatever you have on your stove, right? Heat it from below, it turns over. The turnover time for one of these cells is probably on the order of 500,000 years. So it's geological time frame, it's not instant. On the other hand, 500,000 years is extremely short in geological and certainly age of the solar system time, right? So these are resurfacing, turning over. This is nitrogen ice that is probably a few kilometers thick, turning over. This is not liquid, it's fluid because it's like silly putty flowing over a long period of time, the way that glaciers flow. You'll also notice that there's these sort of black bits that seem to accumulate at the junctions and on the edges. We think those are water ice, little icebergs. Water ice, remember, being lighter, but gets covered in the black gunk, so they're quite old chunks of piece of water. I'll talk about the black gunk in a minute. But that seems to be accumulating at the boundaries, a bit away the scum on your soup. I hate to suggest that your soup might have scum in it, but you know what I'm talking about, right? When you hit, sometimes the chunky bits accumulate where the turnover. Next time you make some soup, try that out and see if have a look. Put some pepper on top of your bubbling soup and see what happens. Okay. So these are convection cells that seem to be turning over. And this is consistent with various models that people have done of ice turning over. This is actually for Callisto, but the same thing applies here. And you can see in Sputnik Planum all of these cells, which we think are nitrogen ice convecting. This is a zoom in, again, one of these pieces of chunks of water ice accumulating at the boundaries. You can see a boundary here. There's something that looks like this surface is like snow that's aged maybe or been blown. It sort of looks like the wind would be blowing it like it would be snow dunes or something. The pressure of the atmosphere is very weak, so it's unlikely that right now there's enough pressure to really move stuff around, but maybe in an early era there was more atmosphere. So this is a movie of the flyby. We're on the spacecraft, we're flying by. This is Sharon going around. We're going to go between Charon and Pluto. We're going to take pictures of Pluto, and then we're going to turn back and look at the sun and the Earth, and we're going to look through the atmosphere. And these occultation measurements, looking at the sun through the atmosphere, are going to be very important for working out what's going on with the atmosphere. So this is an example, and think of the white lines going through the sunlight observed by the UV instrument ALICE is high, and then it drops down quite a long way away from Pluto, drops all the way down, so the sun sets, then the sun rises again, and you can see there's absorption of quite a lot of sunlight a long way away from the planet. And then if you reverse in and out, you end up with these red and white lines on top of each other, which tells us the atmosphere is pretty symmetric. That's all that does. But what's interesting is the large amount of light that's absorbed further around the outside. Pluto is a low gravity compared with the Earth, and so we expect the atmosphere to move away, not to be so tightly bound, even though it's quite cold. But what was interesting is that we really expected this atmosphere to be even further extended, and it turns out that it's quite cold higher up. Something is cooling it off at high altitudes. I'll come back to that in a minute. So what's going on? When we look through at the sun, this is a visible light, what we see is a blue sky. So we're seeing scattering of sunlight, preferably the blue part of the spectrum, the same way we have blue skies above us here on Earth, because of scattering by aerosols or molecules, very small molecules that make these make this blue color. But it's really extended quite a long way out, and if you look carefully, you can see there are multiple layers of haze there. So these hazes are really quite dramatic. And if we zoom in really carefully and we analyze it in detail, these hazes extend for up to 50 miles from the surface, all the way around, and these layers of hazes there are very thick and multiple. So what's happening is ultraviolet light from the sun is coming in, it's hitting methane, CH4, and we're turning it into materials like ethylene and acetylene. So two carbons coming together, they rearrange the hydrogens and then bring in more of these. And you can imagine that as this stuff is falling out of the atmosphere, you begin to make these aerosols of hydrocarbons that are raining out and hitting the surface, right? So this is the black stuff, the brown stuff, right? We know this because in the lab, when we take methane and CO and nitrogen and we hit it with UV light, maybe some energetic particles like the solar wind out at Pluto, we make this stuff which Carl Sagan and his colleagues called tholins, which is basically brown, oily, gunky, yucky petroleum products, basically. It's not made the way petroleum products are, but it's the same sort of material, oily, gunky stuff. And so here, the older areas, the water has had this stuff raining out of the atmosphere for billions of years, making a thick, oily, gooey layer. The fresher areas, where no craters are, younger bright surface, is fresh deposits of nitrogen and methane ice on top. So this is all now beginning to come together and make some sense. And when we look with the spectrometer on the Ralph instrument, we can begin to work out these compositions. Let me do this. Why is this not? Come on. Okay. So, looking in closer, these are convective systems of nitrogen ice here, but away from that, you can see these big chunky blocks. You can see there's accumulation of the brown gunky tholins in between, and then the layers are actually of dark stuff. So you can almost see like stratigraphic layers where this is broken up, that maybe there's been episodes of this material coming down, then it gets broken up, and then more episodes. So just like geology on Earth, where you accumulate layers and then you break up and expose the different layers. It's going to take a while to work out exactly the sequence of all this. Okay, so as I said, we were actually expecting a very extended atmosphere like this. In fact, because the outer layers of the atmosphere are a lot colder, and we observe this with the radio and the UV occultations, that it's colder, you end up with a much smaller atmosphere, much more like this. So why? What is it in the outer atmosphere that is cooling it off? Okay. Well, it turns out that around the time of the flyby, we were able to use, a group of astronomers in Paris used a telescope that's down in Chile called ALMA, it's in the millimeter part of the spectrum, to look at Pluto and saw some stuff. Hydrogen cyanide, HCN. Right? Very simple molecule, very nasty. But it turns out that that molecule radiates out heat and cools the outer layers of the atmosphere off, and so shrinks the atmosphere, so it's much smaller than we thought it was going to be. So these has sort of happened at the same time, and it sort of makes sense. So, lesson for global warming. Very easy. All we have to do to cool off the atmosphere is to put hydrogen cyanide in our atmosphere. Great idea, eh?
Takes care of two problems. Cools the
Luckily, it wouldn't work. It would break up. But anyway, it just something to think about. Okay, so what I was interested in is the interaction of the solar wind with this atmosphere. We made a lot of measurements, and we flew through. We were thinking that it would be a lot bigger and we would have something more like a comet. But it turns out that if you, I took the MAVEN material that was being put in the press releases last fall, and I scaled and I looked at Mars and I did the math, and I said, wait a minute, the size of the exosphere of Pluto is comparable, the outer layers of the atmosphere, comparable to the size of Mars. So the interaction of the solar wind at Pluto is in fact about the same scale as the interaction with Mars, which is kind of cool. So it's not so much like a comet, more like a Mars-like atmosphere with about 10 to the 25 molecules escaping per second. Okay. Okay, so these are the hazes. This is one of the cool pictures. We're flying away, we're looking back, we're taking some pictures. You can see the mountains, you can see Sputnik Planum. And if you look at right on the edge here of the shadow, what's really cool is you actually see crepuscular rays. These are mountains that are sticking up and making shadows. Right? Can you see this? Really cool. The way we sometimes get crepuscular rays when the sun's setting over the flatirons. There. We zoom in and we have this fabulous picture showing these mountains. These are mountains made out of water ice, acting like rock, sticking up a long way, and then these nitrogenized plains here of Sputnik Planum. And then we saw these. Tracks, dinosaurs, wormholes. They're pretty big. I mean, you look at the scale. These are sort of the size of CU's campus, right? I mean, maybe even Boulder. I mean, these are not tiny. Very bizarre. Here's a bunch more. Clustered. Patterns. Any ideas? If you do, write it up, publish it in Nature.
The rockets, we go up into the mountains in the summer, and the snow has been exposed to the sunlight, and you get these sun cups, maybe even these kind of tentacles where you've got, this is basically sublimation, the sun hitting the snow, it's evaporating, disappearing, and it over time makes these sun cups. So this is the sort of thing that we see after a long summer of exposure of snow. Imagine, even though the sunlight is 1,000 times weaker out of Pluto, but imagine that you have the snow sitting there for millions of years, right? You can then maybe see how you might make really big features. associated with sublimation. So much of the geology that we're seeing on Pluto may actually be more similar to this, associated with sunlight hitting the snow. And then we get this. This is called an ice volcano. What on earth is an ice volcano? I don't really know. I mean, all we know is this thing's about 2 miles high, and it looks like something comes spewing out of here. Maybe deep down it gets hot enough that it vaporizes and comes out. You know, we don't know.
What is the color scale on the left?
The color scale on the left is altitude, and so you can see this one is supposedly 2 miles high. This one actually is 3.5 miles high. Okay. So I mean, yes, you're right. I should have the color scale, but you know, this is the scale. Okay. So this is pretty big, not small mountains. Okay, and then we have the snake skin. Any ideas? So again, maybe sublimation, sunlight persistently hitting one side, causing it to move around, maybe. I'm making this up, we don't know. But this could be methane ice that is much more volatile, easily moved around. Okay? Okay. And then the Sharon. Sharon is mostly geology, very little of the volatiles. They've escaped, doesn't have an atmosphere. It has all sorts of interesting geology, cracks, lots of impact craters, but it doesn't have the glacial features that Pluto has. We have these moons, all very small. This is Sharon for scale, and this is the coolest thing. These are their orbits. Look at Hydra. Spin, 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 spin. Look at that. So this is Pluto and Charon, right? Spin face locked, totally rigid. They're not. There's no tidal heating there. It's absolutely rigid, just like a stick between them. But these things, cool dynamics. Just discovered a paper waiting to be written, or 20 papers waiting to be written. I don't know. You see, very interesting. Who knows what's going on there? You get hypnotized, right? Okay. Okay, so where did we go after Pluto? Well, we flew by Pluto July 2015. We're on our way. You remember that movie I had with all the Kuiper Belt objects? Anybody know why in the direction of Pluto and beyond and opposite, it's really hard to detect Kuiper Belt objects? Why is it hard to look in that direction? We want to see something move relative to the stars.
Oh,
And this
because
is,
right now, Pluto's the center of the galaxies, you know, the
It's
side
at
of
this-
Pluto.
right.
So you have stars.
You've got the Milky Way in the way. Right. So it's hard to see Pluto move and the Kuiper Belt objects moving relative to the Milky Way. But we did look, we got some time with Hubble, and we found an object called, it's called 2014 MU69, or Jim Green. This is the Jim Green who runs NASA's Planetary Science Division, because we want him to give us money keep looking at this object. And I'm standing here with an exercise ball, which is the size of Pluto. That's the size of Pluto. Then Jim Green is about the size of a golf ball. So you can see it's pretty small. And what makes that really interesting is that Pluto is an example of a large Kuiper Belt object that has gone through all these changes, differentiation, a lot of geology, and so on and so forth. It has an atmosphere. Whereas Jim Green, this little one, will be much more, we think, like a original chunk that was scattered by Uranus and Neptune as they migrated out, if those theories are right. And so we want to go and look at another object and see how it compares with Pluto. So it'll get there on January 1st, 2019. Whether or not we look depends on whether or not we are allocating funds to analyze the data. Okay. So I just want to leave you with a really cool picture. This is a recent picture that was delivered to the website, and you can go to this website and look at these pictures. It's really cool to see the different layers of ice. Maybe more recent folds coming over out here, ice underneath, and then you can sort of peek through to see maybe dark areas underneath. So really cool. A lot of work to understand all this. We've got a long way to go. Thank you very much. But I want you to put these on, right? Red is left. So while you're looking at these 3D pictures, I can answer some questions. Yes?
So I'm not a geologist, but it looks like a lot of those features were thermal driven, like plate tectonics. What's the theory of the source of heat in the center of Pluto?
Okay, so you remember that cross section that had a layer of rock inside, 2/3 was rock, and then you have a very thick layer of water ice on the outside. Solid water ice is very poor thermal conductor of heat. And so you have radiogenic heat going on inside that is slowly getting out. Okay? It doesn't take much because nitrogen ice is very volatile and very low viscosity to turn that over. And so we haven't done all the numbers because we don't know the true viscosity or the thermal properties of nitrogen ice at 40 Kelvin with little bits of tholins and methane and so on mixed in, right? There's more work to be done there. But I think the chances are pretty good that the source of heat is probably just internal like that. Yeah, good question. Yeah.
Some of the features you showed, it looked kind of like, and I was wondering if it was because of the shadow, that they look kind of the head direction,
Yeah.
or because there's some kind of weather or some kind of effect?
Well, the snake skin where you saw those little features, we think that must be associated with the sunlight heating one side and cooling the other side, and associated with that. The winds are really not strong enough. So you probably all know that The Martian, the biggest mistake in the movie The Martian is that the pressure of the atmosphere really could not blow open the doors and blast open the tent and all the things that happened in The Martian. There's no way at a millionth of the pressure of this atmosphere that you could have strong winds on the surface of Pluto. So it's unlikely right now, though there could have been in some earlier time winds, it's more likely to be sublimation. And thinking about how sublimation works on time scales of millions of years is a good question. So we have to think that one through. It's a new experience, a new world, totally new world. Okay, any other questions? Yes?
Beyond Jim Green, has there been any discussion of further use of data as the craft keeps going on?
Yeah. So we're hoping that we will continue measuring the solar wind in particular, because the instruments actually measure the ions that come from interstellar space and come into our solar system, become ionized and then carried by the solar wind. And the instrument on Voyager really is not as good at measuring that, or basically cannot measure it the way the instruments on New Horizons. So we will continue. We won't catch up with Voyager. It's moving too slow. And whether or not it survives all the way out to the distance that Voyager is right now, at 120 times the distance from the Sun, not clear. But we will make some measurements as we go. Funding, be willing. So we'll see how that goes. Yeah.
You mentioned that all of the observation sequences had to be pre-programmed and everything because of the long time. What was the sort of the drop dead time before the encounter? When was the last opportunity to update things? And did you have a chance to respond to anything that you were seeing on the approach?
What we did was, there were two things. One thing was, because Pluto hasn't gone around the Sun once since first detected, we didn't actually know the distance of Pluto from the Earth accurately to better than a radius. So think about it. You're going to take a picture of something, but you don't really know where it is. So you're going to go click, 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 because it could be here, it could be here, it could be there, right? We don't know where it is. So you have to take pictures all around. So as we went in, we had refinements on that measurement a little bit, so that can help us up with our sequence. The other thing is we were worried about hitting a debris field. And there was a time, I think about 10 days out, where they looked at all the data, they sat down and had a conference. They brought in NASA headquarters and said, do we go, not go for our nominal trajectory? And they decided to go for it. Because it turns out that it didn't look like there was debris, and the dynamicists said that was the best place. And we had programmed in that the spacecraft, just before it went through the debris, the potential debris field through the ring plane, it would turn back to the Earth and say, here's my best picture, and then go. Right, so we knew we had one in the pocket. Scary. Okay, let me just move this forward one more.
Question about this?
Oh, yeah, okay, I think I can go back. Question about this, yeah?
Yeah. It looks like there's movement there or something, or weathering, a lot of weathering, but if there's not much air.
Doesn't that look like a river?
Yeah.
Huh?
Well,
So,
now it looks like a canyon, but maybe
Yeah,
it's
yeah,
glasses,
yeah.
and
Yeah,
there's that
yeah.
hole there to
Yeah.
the left.
doesn't this look like a lake?
Yeah.
Okay, so nitrogen.
What is that?
Nitrogen, solid nitrogen at 40 Kelvin. How warm does it need to become liquid nitrogen? Anybody know the temperature of liquid nitrogen? 70, right? So you've got to raise the temperature 30 degrees. Woohoo, that's quite a lot. But maybe the seasons are kind of wacky on Pluto. You could imagine this tilt, varies like the tilt does on the Earth and Mars. You could imagine a time where you end up where you have this big exposure to sunlight for a long time. Maybe that would do it. Or what about the fact you've got methane in the atmosphere, greenhouse gas, CO, greenhouse gas? Could you maybe heat the temperature up at the surface just enough to make liquid nitrogen for a little while to maybe make it bigger? Would you buy that argument? If I published that in Nature, will you? Okay, yeah.
One question, please. Do you have the data from SDC that was gathered during the past?
It's in the computer somewhere in this building.
Do you have also?
Do you know what we detected?
Yeah.
One particle. Statistically significant, one particle.
During the past.
Over 5 days.
So what density is that?
We calculate the density. It's in the science paper that I'm about to publish, and I forget. It's tiny. It's like 1 per 6 kilometers. I can't remember the number.
Do you have all the data back?
No, we only have about a quarter back. But we're going to get a whole bunch more. Now, we got some of the best back. Right, the best pictures are probably back. We're going to have a few more pictures, quite a few more pictures, but also a lot of spectroscopic data, and we're going to resend some of the stuff. That, we're going to be looking at the sides were a little more fuzzy because they're further away. Some of that sort of stuff as well. There'll be a lot more stuff coming back.